welcome to the first in a series of videos on epsilon-delta proofs. My aim in these videos will be to show you a wide variety of examples of how to use the formal epsilon-delta definition to provide rigorous proofs of limits. Okay? We'll start with the basics, and then we'll do harder and harder examples as we go on. Okay, so let's start with figuring out how the formal definition of limit even comes about. Okay? So if you look at the blackboard here, we have a function f of x, and by definition, the limit as x approaches a of f of x, that equals L. What that means is, in an informal sense, that f of x, the value of the function at x, can be made as close to L as we want by choosing x sufficiently close to, but unequal to a. Okay? So what that means is, as you choose x values which are closer and closer to our point a here that we're considering, the values of the function f will be closer and closer to L. Okay? What does that mean formally? We can make f of x as close to L as desired. Okay? So the distance between the function f of x and what we believe the limit to be, L, can be made as close as desired. Okay? So that distance between L and f of x, which is f of x minus L, okay, in absolute values. The absolute values are here just to make sure that this quantity isn't negative, because as you see, sometimes f could be bigger than L or less than. This will just give us the distance. So this difference, f of x minus L, can be made as small as desired. What does that mean? Well, it can be made less than 1, less than 0.1, or less than epsilon for any positive quantity epsilon. This can be made less than epsilon, okay, as long as x is chosen close enough to a. What does that mean? F of x minus L is less than epsilon as long as x minus a, the distance between x and a, is less than some other quantity, which will most likely depend on the size of epsilon. We call that delta. Now lastly, x cannot be equal to a. It just has to be really close to it. So we put that in there. Okay? So let's just write this out formally. F of x minus L is less than epsilon as long as 0 is less than x minus a is less than delta. Okay? This is true for any epsilon. For any epsilon at all, we can find a delta value for which the statement will hold. Okay? So for any epsilon greater than 0, okay, there exists a positive delta value. There exists a delta greater than 0 such that 0 is less than x minus a is less than delta implies f of x minus L is less than epsilon. Okay? So graphically, what does that mean? Well, we have a little epsilon window around L. Remember, f of x minus L in absolute values less than epsilon means the same thing as f of x belongs to the little window L minus epsilon to L plus epsilon. So let's say our little epsilon window is here. Okay? There's our L plus epsilon. There's L minus epsilon. Okay? The value of the function will fall within this little epsilon window around L. Okay? As long as we choose our x's to be close to a. Okay? So graphically, that means that our little delta window around a has to look something like this. Okay? So there's our a minus delta, and there is a plus delta. Okay? And for any x which is within this window, if we feed that little value of x into the function, it will map to a point on the function which falls within the epsilon window around L. Okay? If we map that x up, it also falls within the little window. Okay? And if we map the edges, the boundaries, they fall exactly into the window. Okay? We don't necessarily have to have these to be exactly intersecting. Okay? The little window, the delta window around A, could be much smaller, as long as everything within it falls within the epsilon window around L. Okay? So that's how the formal definition comes about. This here is the formal definition of what it means for the limit as x approaches a of f of x to be equal to L. Okay? What that means is that for any given epsilon greater than 0, there exists a delta greater than 0, such that if x falls within the delta window around a, but is actually unequal to a, then the values of the function f of f at that x will fall within the epsilon window around L. Okay? So let's use this definition to do a few examples. Okay, let's prove some basic limits. I erased the board, as you can see, and wrote down the formal definition of limit here symbolically. Okay, so we have it for easy reference. Right? So let's do a simple example to start off with. Okay, let's use the definition to give a proof of a limit. Okay, let's say that our function is just a linear function. Okay, so let's say, call this example 1. Okay. So suppose that f of x is equal to, say, 2x plus 1. Okay? Nice line with a slope of 2 passing through 1. Okay, we all know what that looks like. And let's prove that the limit as x approaches 2, let's say, of this function, 2x plus 1, equals 5. Okay? Proof. So according to the definition, we want to show that for all epsilon greater than 0, we can find a delta greater than 0, such that this implication will hold. Okay? So the first line in our proof should be, let epsilon greater than 0 be given. Okay? Writing this shows that you have no control over what epsilon is. And the proof that will follow will be valid for any epsilon. Exactly what we want to do. Now, we want to show that for this arbitrary epsilon, we can find a delta. So, let delta equal something. Now, I'm not going to fill this in yet, because I don't know what value of delta will work yet. That'll become apparent once we start working through the proof. And then we'll come back and fill that in later. And the last line will be, let x satisfying this inequality here, 0 less than x minus 2 in this case is the value being approached, less than delta, be given. Okay? So again, we have epsilon greater than 0 given, so the proof will work for all epsilon. We have a specific delta. This will be filled in later as we go through the proof, because we don't know what delta is yet. It will surely depend on epsilon. As epsilon gets smaller, delta will also have to be smaller. But how small will it have to be? We'll find that out. Okay? So we have epsilon arbitrary, a specific delta value dependent on that epsilon. That satisfies this there exists part in the definition. Okay? Such that 0 less than x minus a less than delta implies this. So if x satisfies this criteria, okay, let x satisfy that criteria, we will have f of x minus L less than epsilon. Okay? So these three lines should precede any limit proof. Now the actual proof will begin, and hopefully we'll get it all in one line. Okay? We'll start with this statement now, and we're going to make that less than epsilon for our function. Okay? So f of x minus L, in our case, is going to be the function, so 2x plus 1, that's the function, minus the limit 5, okay? We're going to show that that quantity is going to be made less than epsilon. Okay? So let's do this. Let's do some algebra first. 1 minus 5 is negative 4, okay? So this is going to be 2x minus 4 in absolute values. Now, there's a common factor of 2, so that can come out. So we have 2 times x minus 2. And now, we're ready to use the given information. What's given here? x satisfying x minus 2 less than delta is given. Okay? So this quantity, this x minus 2 here, is less than delta. Okay? So this is less than 2 times delta. Okay? Now, we want to choose delta such that this will be less than or equal to epsilon. It could be equal to epsilon, because if it is, we have f of x minus L less than epsilon by that inequality. So if we choose delta so that 2 times delta is going to be equal to epsilon, we'd have finished the proof. Okay, and that's exactly what we're going to do. So we have 2 times delta here, which is going to equal 2 times epsilon over 2. And now the 2's will cancel out, and you'll get epsilon at the end. And that'll be the end of the proof. So which delta do we need to choose? Epsilon over 2. Okay? And that's the end of the proof, square. So let's go through this again. Why is this a proof? Okay? Look at the definition one more time. For all epsilon greater than 0, there exists a delta greater than 0 such that this inequality implies this inequality. Okay? Let epsilon greater than 0 be given. Epsilon can be any value greater than 0. If you want, you can substitute a value. Say 0.1 is our epsilon. Let delta equal epsilon over 2. So now we have a specific value of delta. If epsilon equals 0.1, then delta will be 0.05. Okay? Let x satisfying 0 less than x minus 2 less than delta be given. Okay? So again, x is really close to 2, 0.05 away, if we use that as our epsilon, 0.1 as our epsilon. And then we show that given this information, this line holds. Okay? F of x minus L, we're subbing in the function, we're subbing in what we believe the limit to be, and we go through the algebra. And if the limit value, the L value that you've chosen, here it's 5, is in fact correct, then some algebra, some manipulations will lead to a constant perhaps multiplied by a quantity that we know something about. In this case, we know that x minus 2 is less than delta. Okay? So we'd have that this is equal to a constant times our value, which can be made less than delta. And as soon as we have that in our proof, as soon as we lose all of our x's in this line here, and just have f of x minus L bounded above by something multiplied by delta perhaps, or some expression involving delta, then we can equate that to epsilon and then solve in our heads for the delta, which will make it work. And then we can pretend to sub that delta in. Okay, so in this case, we solve that delta has to be equal to epsilon over 2, okay, in order for the proof to follow. 2 times epsilon over 2 is in fact epsilon. So we have our proof in one nice long line. F of x minus L, algebra, 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 use the given information, use the delta, okay, less than epsilon at the end. And that's the end of the proof. All right, let's do another example. Look at this. Not everything needs to be wiped away. I'm going to wipe away this stuff over here, that, and that. All right? Now we're going to choose a different function, and these 3 lines should start off any limit proof, as I already said. We'll just choose a different function, and then we'll fill in the proof for that. Okay? So let's do a function, here we did a line with a positive slope. Okay? Let's do just a horizontal line, f of x equals c, where c is any constant. Okay? So let's change f of x to c, okay? And we're going to prove that the limit as x approaches, let's say instead of 2, we're going to change the value of approach to a for an arbitrary a. We're going to prove that the limit as x approaches a of f of x, which is in this case c, so I guess I better just write that, limit as x approaches a of c equals c. Surprise. So let's go through the proof, okay? And this is going to work, by the way, for all a in the real numbers, okay? And c here is also any real number, okay? So we'll do a fairly general proof. The limit as x approaches any value of any constant function equals the value of that constant. Okay. First three lines, as usual, let epsilon greater than 0 be given. Let delta equal something. We're going to fill that in as we did before. Let x satisfying 0 is less than x minus a is less than delta be given. Now f of x minus L, what is it in this case? Well, f of x is c, and L is also c, okay? So we have c minus c in absolute values, which equals 0, okay? And we're done. 0 is less than epsilon for any epsilon greater than 0. And that's the end of the proof. So this is perhaps a little tricky because it's so simple. What value of delta here do we choose? Well, in this case, delta didn't enter the proof at all, right? There was no need for it. The quantity inside the absolute values was always 0, and we could jump right away to the epsilon statement. So in this case, any delta that we fill in here will be okay. Like pi, for example, we can let delta equal pi, and the proof will still work. If you feel uncomfortable with this, if you really desperately want to use delta in the proof, you can always change it up, do something like this. 0 is less than delta, because every delta is greater than 0, and we can set that equal to epsilon. Okay, that proof works as well. So delta can be equal to epsilon. But again, there's no need for that. So why this strange situation here, where the delta doesn't even come into the proof? Well, let's try to visualize this. So if we draw a little Cartesian plane here, what we have is our function being just a constant, okay, c. So there's f of x. And let's say our a value is over here somewhere. There's a. Now, f does not change its value. It's always equal to c. So it doesn't matter how far away from a we are with our x's, f maps all x's up to c. So the distance between f of x and this limit, which is 0 all the time for any x value, does not depend on the x value. It does not depend how far the x's are from a. We could pick x's out here, or we could pick x's really close to here, okay? If we have delta being equal to epsilon, for all epsilon, then what that's saying is that the size of the delta window around a will be proportional exactly to the size of the epsilon window around f, okay? As we make this distance smaller, this will have to be smaller proportionally. We don't have to do that. As this distance gets smaller, this distance could remain fixed at pi, as we saw before, or any other value, and the difference between f and c will always fall within the epsilon window, of course, because the difference is always 0. In the other situation, delta did need to depend on epsilon. Why was that? Well, what did we have in the other situation? We had, there's our Cartesian plane. It was 2x plus 1, so there's 1, and we had a line, slope of 2, okay? And we claimed that the limit as x approaches 2 of that function equals 5, okay? So if we chose, in our first example, a little epsilon window around 5, let's say that's our epsilon window. It looks like it's about length 1 here, okay? Then we'd need our deltas to be chosen a half distance around 2, okay? We'd need our delta window to be smaller here, so that everything that's being fed into the function from this delta window gets mapped into the epsilon window. And obviously, since the slope of the function is 2, okay, we'd need to choose values twice as close to 2 in order to have them fall within this little window, epsilon around 5, okay? If the line had a higher slope, we'd need to be even more careful here. The higher the slope of the line, the smaller this window will be compared to this window. And the proportion will be exactly the slope of the line, okay? So let's do a more general example now. Let's prove that any linear function has the expected limit, okay? So example number 3, I guess this would be. I forgot to change that number before. So this is example number 3. And we're going to do f of x being equal to mx plus b, so a general line. Okay? mx plus b. M and b are real numbers. And we're just going to stipulate here that m is not equal to 0. Okay? We just covered that case where m is equal to 0. Okay? So the slope is non-negative. Okay? And we're going to prove that the limit as x approaches a for any a of our function mx plus b is the expected value ma plus b. Okay? Value given by just substituting a into the expression. So let's go through that proof. It won't be much more difficult than the first example we did. Okay? Except we'll just be doing things in terms of MB and A in this case. Okay? So let's go through the proof. First 3 lines remain the same as usual. And f of x minus L in this case will be what? Well, our f is mx plus b. Our L is ma plus b. So we have mx plus b minus ma plus b. There we go. And we want to show that this quantity will be less than epsilon. So let's do some algebra first. The b's cancel out. And what do we have? We have mx minus ma. And the m is common and it will factor out. So we'll have m times x minus a inside the absolute values, which, by the way, is equal to the absolute value of m times the absolute value of x minus a, because an absolute value splits over a product of real numbers. And we have a similar situation as in the first example. We have our x minus a quantity, which we know something about. We know that to be less than delta. Okay? And instead of having a 2 in front, we have an absolute value of m. So all we need to do here is, first of all, use this given information. So this line over here is less than absolute value of m times delta. And now we want that quantity to be equal to epsilon. Then this line will be the proof. We'll have f of x minus L, algebra, 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 being less than epsilon. Okay? Algebra plus given information. In order to make that equal to epsilon, what do we need to choose delta to be? Epsilon over the absolute value of m. Then the absolute values of m will cancel out, and we'll be left with what we want. Epsilon over m. And the m's cancel out, and you get epsilon at the end. And that's the end of the proof. So delta is epsilon over m. Now just make sure we didn't make any mistakes. Delta should be positive, epsilon is positive, and m is also positive. If you take the absolute value, of course. M itself could be negative, but absolute value of m is positive, and non-zero by that stipulation. Okay? And the rest of the proof works, as you can see. Okay? Thanks for watching.